Bismillahirrahmanirrahim. This is the 11th lecture, and today we will start with the three very common operating conditions for the Zener diodes. So we will start with slide number 18. Title of the slide is Response of the Zener diode to different operating conditions. Now, the use of Zener diode as a regulator is so common that three conditions surrounding the analysis of the basic Zener regulator are considered. The analysis provides the response of the Zener diode to three different operating conditions, and these three different operating conditions include: the first operating condition is when the input voltage is fixed and the load is also fixed. That is, input voltage Vi and R are fixed. And then we will study the second operating condition where the input voltage is fixed but the load resistance is variable. Therefore, second operating condition is fixed input voltage and variable RL. And the third operating condition is that fixed RL and variable input voltage. That is, we will have a constant load resistance RL, but the input voltage will be variable. So now let us come to the first operating condition and see how to analyze such operating condition. So the first operating condition is that we have input voltage and load resistance are fixed. Both are constant. This is the most simplest Zener diode regulator network, and the circuit diagram is shown in diagram number 2.112, where we see the input voltage. This input voltage is fixed. Then we see a series resistance R and our Zener diode and a load resistance RL. The simplest Zener diode regulator network appears in figure 2.112. The applied DC voltage is fixed, as is the load resistor. The analysis can be fundamentally be broken into two steps. So to analyze this circuit, we will break down our analysis in two steps. Remember that we have an input voltage fixed and the load resistance is also fixed. So we can say that the entire circuit is a constant. Now, the first step to analyze such circuit is that determine the state of the Zener diode by removing it from the network and calculating the voltage across the resulting open circuit. That is, our first step is, if we look at figure 2.113, we purposely remove the Zener diode. As shown over here, we purposely remove the Zener diode. And then we find the voltage across the Zener diode. That is, in this case, we will find the voltage across VL. VL is equal to our standard, solving our standard series network, that VL is equal to RL into VI divided by bracket R plus RL. So this is the voltage appearing across VL without the Zener diode. Now, after performing this step, we have to make a decision. If the voltage as calculated in our first step, as shown in equation number 2.16, if this voltage is equal to or larger than the Zener voltage that we had removed, if V is larger than or equal to Vz, then the Zener diode is on, it is working, and the appropriate equivalent model can be substituted. That is, if by removing Zener diode, if the voltage across VL or V load is larger than the voltage of the Zener diode, then we say that the Zener diode is on, it is working, and we can approximate and we can replace the model. But if the voltage, load voltage or V, is smaller than the Vz, that is a Zener voltage of Zener diode, then the Zener diode is off and the open circuit equivalence is substituted. So we have to make a decision whether the voltage appearing across the load is equal to or larger than Vz or it is smaller than Vz. If the voltage is larger than Vz, then we can continue with the analysis, and we can say that since the voltage across VL is larger than Vz, so when we connect the Zener diode, then the Zener diode will be turned on and the voltage in fact across RL will be equal to Vz. But if the voltage V is smaller than Vz, that is the Zener diode voltage, then we will say that the Zener diode is not turned on and it is equal to a open circuit. Now comes the second step. The second step is substitute the approximate equivalent circuit and solve for the desired unknowns. That is, if our voltage across the load is equal to or larger than Vz, then we will substitute the voltage of Zener diode as our load voltage. And we will say that VL is in fact equal to Vz, that is a Zener diode, because without using Vz, it will be larger. Therefore, the Vz will experience breakdown and the practical voltage across load resistance is Vz. So now we come to figure 2.114 and we say that since the voltage of the load is larger than Vz, therefore our Zener diode is operating and we replace the Zener diode with the equivalent circuit. Now, the Zener diode current must be determined by application of Kirchhoff's current law. That is, current in IR is equal to IZ plus IL. This is the current IR. This is equal to the current in the Zener diode branch plus the current in the load resistance branch. Or we can say that IZ is equal to IR minus IL. And IL is very simple to find since IL is equal to VL over RL and IR is equal to VI minus VL over R. Remember that VL in this case is equal to equation number 2.17. VL is equal to VZ. And then lastly, the power dissipated by the Zener diode is determined by the voltage across the Zener diode multiplied by the current flowing through the Zener diode. That is equation number 2.19. Pz is equal to Zener diode voltage multiplied by IZ. And this power should be smaller than or should be less than the PZM specified for the device. PZM is the maximum power dissipation that a given Zener diode can dissipate, and this information can be gathered from the data sheet provided by the manufacturer. So this was our first operating condition. And now we will come to example number 2.26. The statement of the example is part number A. For the Zener diode network shown in figure 2.115, determine VL, VR, IZ and PZ. And then part number B is repeat part A with RL equal to 5 kilo ohms. Now this is figure number 2.115. It has the input voltage of 16 volt. Series resistance R is 1 kilo ohms. The Zener diode that we are using is of 100 volts, and the PZM, the maximum power dissipation that can be bared by this Zener diode, is 30 milliwatts, whereas for part number A, RL is 1.2 kilo ohms. So now let us come to the solution for part number A. We will follow our procedure. In the first step, we will remove the Zener diode. In the first step, we will remove this Zener diode. We will assume that it is not present and we have only one voltage power supply of 16 volt and resistance R of 1 kilo ohm and one RL of 1.2 kilo ohms. Now let us find the voltage across load resistance RL, which is also the voltage across the Zener diode if it was present. Now we will solve for the Kirchhoff's voltage law and find that the voltage VL is equal to RL into V input divided by R plus RL, which is equal to, in our case, it is equal to 8.73 volts. Now 8.73 volt for part number A, 8.73 volt are appearing across VL, whereas we have a Zener diode of 10 volt. Now, will this 8.73 volt, will this break down our Zener diode barrier? So the answer is no. This 8.73 volt are not enough to break down the Zener diode barrier. Therefore, our Zener diode will remain open circuit. I will write over here the Zener diode for part number A will remain open circuit. Now, as it is written, since V is equal to 8.73 volt is less than Vz is equal to 10 volt, the diode is in the off state as shown figure 2.117. Substituting the open circuit equivalent results in the same network as in figure 1.116, where we find that VL is equal to 8.73 volt. Voltage across the series resistance VR is equal to 7.27 volt, and current through the Zener diode is 0 ampere. Therefore, the power dissipated through the Zener diode is 0 watts. So this is VL, VR, IZ and PZ for part number A. Now we come to the second part. In the second part, we have replaced RL by resistance of 3 kilo ohms. And now we want to find the voltage across load, the voltage across R, the current through the Zener diode, and the power dissipated through the Zener diode. So in part number B, we will start the analysis with the same procedure. In the first step, we will remove the Zener diode. We will assume that it is not present over here and then find voltage VL. In this case, in part number B, VL is equal to 12 volts. Now this 12 volt is greater than VZ equal to 10 volt. Thus, the diode is now on. It is now experiencing the Zener diode voltage breakdown. Therefore, we will take VL equal to 10 volts. This is the most important equation for part number B. That in the first step, we removed the Zener diode and found the voltage across RL. This voltage was larger than the breakdown voltage of the Zener diode. Therefore, when we replace our Zener diode and return it to the circuit, the output voltage across RL will not be 12 volts any longer. It will be equal to the voltage of the Zener diode, which is in our case 10 volts. So VZ is now 10 volts. Therefore, the voltage VR, the voltage across resistance R, this is VR, is equal to 16 minus 10, that is 6 volt. The current IL, the load current, is 3.3 milliampere. The current IR, the current flowing in the series resistance R, is equal to 6 milliampere, whereas the current in the Zener diode is equal to 2.67 milliampere. And this can be seen in circuit 2.118. Now for the last step, for the last requirement is the power dissipation. Power dissipation through Zener diode, it is equal to voltage across the Zener diode into current flowing through the Zener diode, which is equal to 10 volt multiplied by 2.67 milliampere is equal to 26.7 milliwatts. And since we have been informed that our PZM is 30 milliwatt and our actual power being dissipated is only 26.7 milliwatt, therefore this diode will be sufficient. So this was the case where we have a fixed input voltage and a fixed load resistance and the analysis for the circuit. Okay, so thank you very much, class. Please go through the examples, read the theory. Reading from the textbook is highly recommended, and solve the example that we have done today. Run them in the simulation software also and confirm the results. Okay? Thank you very much. Assalamu alaikum.
Allah Hafiz.